A concentration unit that is more useful in chemistry is called molarity. Because chemists do a lot of things with moles. Have you noticed that? They're always converting from grams to moles. Why? Moles have to do with the number of particles. And in a chemical reaction, the equations tell us relationships between particles, not between masses. So we use molarity a lot because molarity gives us information about the moles of solute in a solution. So molarity, which has the abbreviation capital M, is defined as the number of moles of solute per liter of solution. Okay, so it's a little different than percentage. So it's the moles of solute per liter of solution, not solvent. Now, in these sorts of problems that you'll be given, they rarely try to trick you like they do in the percentage problems. I can pretty much promise you I'll try to trick you on the next exam with a percentage problem. I'll give you the mass of the solution, not the mass of the solution. I'll give you the mass of the solute and the mass of the solvent, and I'll make you add them together. Okay, so you've been warned. I will try to trick you on that. Molarity, we usually don't do that because the trick ends up being way, way too complicated because of volumes and densities and differences in how things mix, and so we just don't do that. So they'll generally give you liters of solution, or they'll give you some other volume unit like milliliters, then you have to convert to liters because these units have to be these units, moles per liter. Making a solution of a specified molarity, generally we put the solute in the flask and add water, and we're going to add the water until we get to the right volume. So it's not like you measure out the liquid and then put the solute in. Because probably from your experience as a child messing around in the kitchen, you can answer this. If you have a measuring cup and you fill it full of water and then put half a cup of sugar in it, what's going to happen? The water's going to spill over the top of the cup because when you put the sugar in, it occupies some space. How much space it occupies is difficult to predict. And so what we do is we mix them and then we just add the water or whatever the solvent is until we get to that volume. Molarity is capital M. Is that a capital M or a lowercase m? Somebody guess. Capital M. No, that's a lowercase m. It's hard to tell, right? And if you had said lowercase m, I would have said no, it's a capital M. Right? Because it could be either. That's a really bad O. It could be either. What chemists often do with handwriting, you won't see this on the PowerPoints or in your book, is if it's a capital M, we'll underline it. So there's no confusion. Because nobody wants to take the time to make all their capital M's really, really pointy, right? Usually a capital M looks just like a big lowercase m. So that's why I'm going to be underlining my capital M's, just so you know. So here's an illustration of how we generally make a solution of a specified molarity. So we use what's called a volumetric flask, which is calibrated to hold a certain volume. I think this one is going to be a 1 liter volumetric flask. It's going to have a mark etched on the neck. The neck is very skinny for a reason. That's because a small difference in volume will be very noticeable. Okay, why are graduated cylinders skinny as opposed to being really fat and shallow? Because you want to see that difference in height reflect the difference in the volume. So the skinnier this neck is, the greater the difference in height when the volume changes. So that makes it more accurate. So this is marked on the neck. What you do is you add your amount of solute. If we're making a one molar solution, that does not mean that there's one tooth in it. It's 1 moles per liter. The molarity is 1. we're going to calculate the mass of 1 mole of sodium chloride because the balance won't weigh in moles. We calculate that 1 mole of sodium chloride weighs 58.44 grams. So we measure out 58.44 grams of sodium chloride. We add it to the container. And then we add water. Generally, we're going to add water about halfway where the volume is still down here in the fat part of the flask. And then we're going to swirl it around until all of this dissolves. We want this all dissolved before we top it off and make the volume just right. Then the problem is mixing this when it's up here. That's when you need a stopper, and you actually have to turn the thing upside down repeatedly. They've done studies, and I think to really be sure it's mixed, you need to invert it 20 times to make sure that it's mixed. Because if you just swirl it around when it's full up like this, it's not going to mix very much at all. So anyway, that's how you make a solution of a specific molarity. So let's do an example of that sort of thing. Calculate the molarity of a solution made by putting 55.8 grams of sodium nitrate into a beaker and diluting to 2.50 liters. This 2.50 liters, is that the volume of water or the volume of the entire solution? It's the whole solution. So this is the volume of solution in liters, so that's liters of solution. That's nice. They gave that to us. So they're saying calculate the molarity. We need to remember what molarity is. Molarity equals moles of solute divided by liters of solution. So that's what we need to find, those two things. Well, we already found the liters of solution. Did they give us the moles of solute? No. They gave us grams. They were nice enough to give us the chemical formula instead of the name, so that was thoughtful. Can we convert 55.8 grams to moles? Yes, absolutely. If you remember, I told you we would be using molar masses a lot. Was I right? Yeah, that's just one of those standby things that we do all the time. So, calculating the molar mass from this formula: 1 sodium, 1 nitrogen, 3 oxygens. And, you know, it's just always a good idea to write it out. 22.99 for the sodium, 14.01 for the nitrogen. These are coming off the periodic table. 3 times 16 for the oxygen. You add them together. 22.99 plus 14.01 plus 3 times 16 equals 85. Which is kind of weird. That's like going to the grocery store and having the bill come out to be exactly 100. I'm going to throw a couple zeros on there because 85.00. All these guys had 4 sig figs. This should have 4 sig figs. That's the mass of 1 mole. So we're going to take this 55.8 grams, and we want to end up with moles, so we're going to divide by grams. We look at this number we just calculated. That is the mass of 1 mole. So 1 mole goes up here, 85.00 goes down there. So we have 55.8 divided by 85. 0.65. This should have 3 sig figs. I'm going to keep a couple extras. 65647 moles. And the 6, the 5, and the 6 are my significant figures. Now we have the numbers we need. The moles of solute, and we're just reminding ourselves with the underline how many sig figs there are in that number, divided by 2.50 liters of solution. A lot of times when you're doing these calculations, you know, you figure this out that number is still in your calculator. So why erase it and type it in again? There's no reason to do that. Just leave it in there. Then you're naturally carrying all the extra digits and you're avoiding rounding errors. Well, I did type it back in again, but divide by 2.5. Now we should round. 3 sig figs, 0.263. What are the units? Moles per liter. Another way to write that is 0.263 capital M. Those are the same. Capital M means moles per liter. Any questions?
So when we're going to do our homework, that's what they're going to accept and the capital M, or is it going to be?
Well, usually on the online homework, they already have the unit written there for you. So, doing something like on a lab where it's handwritten, either of these is fine. I know what they mean. The really important thing is that you recognize that they mean exactly the same thing. So that when you see something capital M and you came up with moles per liter, maybe all the choices had capital M as the unit. Don't let that freak you out, right? Because it's the same thing. It's just like my son's name is Thomas, but we never call him that, right? We call him Tommy. Is that a different person? No, it's just different is all. One day, he will not want to be called Tommy. We're still waiting for that. He's 13. So molarity, just like percent, can be used as a conversion factor. So using molarity in calculations. Here's another type of question. Determine how many grams of sucrose are contained in 1.95 liters of 0.781 capital M molar sucrose solution. When we read this, 0.781 molar is how we would pronounce that. That's making it into an adjective. Well, one of the approaches that we've had for solving these word problems is to take the numbers that are given we'll write down the numbers, and that'll help us to see what we need to do. So 1.95 liters is one of the numbers given, and 0.781 capital M. This is where recognizing what capital M means is really important. That is 0.781 moles per liter. When you write the capital M, it just looks like some unit like meter or something. When you write moles per liter, now this starts to look like a conversion factor, doesn't it? This is what's going to be used as a conversion factor. This is the number we have to start with. We just have to figure out where are we going and how are we going to get there. So I'm going to write a path up here. We're starting with liters, and what do we want to end up with? We want to end up with grams. What does this allow us to convert to? Moles. That allows us to go from liters to moles. And then moles to grams? What do we use to convert there? Molar mass, right? They gave us the formula. We could calculate the molar mass of sucrose, and we can convert moles to grams. So let's start. 1.95 liters. There's going to be two fractions, and this is our little path, liters to moles to grams. So down here we go liters to moles to grams, following the path. This unit comes to the bottom, so they cancel out. This unit comes to the bottom. Dimensional analysis. It's like a dotted line through the class. On again, off again. Well, the moles per liter are from the concentration, the molarity. Always pay attention to what unit is the number with. If you didn't write it like that, if you wrote it 0.781 moles per liter, sometimes students get a little confused about which unit is that number with. It's with the unit on the top. It's always with the unit on the top. And sometimes you'll see it typed out, because it's so much easier, in a horizontal fashion with a slash. I would encourage you not to write it like that by hand, because that takes away from its fractionness. Just made up a new word. This is a fraction. There's a numerator and a denominator, and when you tip them on its side like that, sometimes you just lose that and you don't see it anymore. And it's really important to be able to see that this is a fraction. I think this is the best way, because here the 0.781 is definitely with moles. So we're going to write the 0.781 on the same side of the line as moles. Because you can get your units all in beautiful, and you can still put your numbers in the wrong place. I've seen it happen many times. Now this guy here is a molar mass. So we need to look at this formula and calculate the molar mass for sucrose. And don't be afraid of those big numbers. 12, there's 12 carbons. Well, each carbon is 12.01. And there's 22 hydrogens. It's okay. 1.008. Each hydrogen weighs 1.008. And 11 oxygens. Each of them weighs 16. 22 times 12.01 plus 20. Nah. I typed in the right thing, I said the wrong thing. 12. 12 times 12.01 plus 22 times 1.008 plus 11 times 16. I came up with 342.296. Anybody else get that? Yeah. It always amazes me how I can do one thing and say another at the same time. Now, really, this guy only has 4 sig figs, but there's only those 2 extras. I'm just going to carry them along, because it's not going to hurt anything. It might be good. 342, oh wow, that's really small. 342.296. I've got all my units in, all my numbers in. Now I just calculate left to right. 1.95 times 0.781 times 342.296 equals 521. We should have 3 sig figs, right? Because everything we started with had 3. So that will round off to 521. 521 grams of sucrose. Is that reasonable? Is it possible? Yeah. This solution, 1.95 liters. Water has a density of 1. And so if you put something in it, that'll change its density a little bit. But this is checking the reasonableness of your answer is where estimating can be really useful. And so we can say, well, 1.95 liters is really close to 2 liters. 2 liters would be 2,000 milliliters, which would weigh 2,000 grams. And this is well under 2,000 grams, so it's probably okay. Any questions? When we're looking at molecular solutes, things like sugar or, well, anything that's a molecule, the concentration is going to reflect the concentration of the solute as it actually exists in solution. The thing about ionic solutes is when you say, oh, I've got a 2 molar sodium chloride solution, that is the concentration of the solid before it was dissolved, the concentration of formula units. But when something that's ionic is dissolved in water, it separates into its ions. And so occasionally we need to look at the concentration of the individual ions. So a 1 mole per liter calcium chloride solution, when the calcium chloride, here let's write that up here, when the calcium chloride dissolves, CaCl2, it forms 1 calcium ion and how many chloride ions? 2 chloride ions. So a 1 molar solution is going to have 1 mole of calcium ion per liter and 2 moles of chloride ions per liter. Sometimes this matters. Sometimes we care about this, other times we don't. But we can estimate the concentration of individual ions from the overall concentration if we know that formula of the compound. So determine the molar concentrations of calcium ion and chloride ion in a 0.75 molar calcium chloride solution. Well, we already looked at this, how this dissolves. So CaCl2 will make calcium and 2 chlorides. .75, what should I write instead of capital M? Moles per liter. So this is moles per liter. Moles of what? Calcium chloride, right? Well, if I want to know the molar concentration of calcium ions, I can look at the formula and ask myself, how many calcium ions are in one of these units? Just 1, right? There's 1 calcium ion is equal to 1 calcium chloride. It's from the formula, the subscript here. So we could use that as a conversion factor. You might think it's kind of silly, and it is, but it's okay. It's good to be silly occasionally. There's 1 mole of calcium for every 1 mole of calcium chloride. Now that's some easy math, right? 0.75 molar calcium ion. It's the same. Why do we have to calculate that? Well, let's look at the next one. The other ion, the chloride. Try to leave myself a little more room this time. 0.75 moles of calcium chloride per liter of solution. Now we want to know the moles of chloride ion per liter of solution. So we're going to multiply by moles of chloride and divide by moles of calcium chloride. How many moles of chloride are in 1 mole of this? 2. There are 2 moles of chloride ions in every 1 mole of that. So this solution is 1.5 molar in chloride ion. Any questions? These conversion factors here are coming from the chemical formula itself. You look at how many of that ion in one of these units. It's just going to be the subscript. There's 2 chlorides and 1 calcium. And so that becomes the conversion factor to figure out how many of the ion. So you'll probably see some questions like that in the homework.